So now that we've introduced the Schrödinger equation, we're going to introduce our first model system that we're going to look at. So if we go back to the Hamiltonian operator, right, that's at the heart of our Schrödinger equation, it has this first term that represents kinetic energy that we just looked at, right, the second derivative, negative h bar squared over 2m, and then there's the potential energy. And so for our simplest system that we want to look at, we want to consider a case where we can get rid of one of these terms. And so that would be to set the second term equal to 0. Now we can set it equal to 0 at all x values, and that's what's known as a free particle. And there are solutions to this. We're going to look at a slightly different version of this. So not the free particle, but a particle confined to a specific area in space. And so we'll represent this with this plot here, energy increasing here, and these lines here represent potential energy. And so our particle, so whatever it is, an electron or whatever, is trapped inside of this potential well, we'll call it. Inside of the box, the potential energy is 0. And so that satisfies keeping things really simple. And outside of the box, the potential energy is infinite. So the particle literally cannot leave the box by definition. And so the way we represent this mathematically is that we say that v of x is equal to 0 when x is between 0 and a, and x is the distance along the box down here, and we'll define the left side of our box to be equal to 0 and the right side of our box to be equal to a. So the length of the box is a. And then v of x, the potential energy, equals infinity everywhere else. So any place where we're not inside the box, the potential energy is infinite. And so we can, this is sort of an idealized system. This is not something that occurs in the real world. We can't create infinite potential wells and things like that. But a close approximation in chemistry is that if we take a conjugated organic molecule like this, we can think about the electrons that are in the pi orbitals, in the pi bonds, are free to travel all along the length of this molecule. And so this electron basically can't leave the molecule. It can, of course, if we give it enough energy and we ionize the molecule. But if we are considering sort of normal energies, we're not ionizing it. The electron cannot leave the molecule, and so stuck inside, and it can travel anywhere along the length. Now, of course, it's not completely flat, this potential, and so this isn't an exact replica, but this is a similar idea here. And so this is the first model system we're going to look at, and we're going to look at finding what are the wave functions and what are the energies associated with this system. But first, to understand this a little bit more, let's talk finally about a little bit what is a wave function, what does it represent. That'll be the next video.